Good afternoon. Today I will talk about a framework that we've developed using the AWR and National Instruments software and hardware for developing wireless LAN solutions for 802.11ac. As a brief history of the 802.11 family of standards, they started back in June of '97, which seems a long time from now, with the and then in September '99, the 802.11a and 802.11b were released, followed by GN in 2003 and 2009, and finally in January 2014, the 802.11ac was ratified. The 802.11ac is also known as the very high throughput, or VHT, because it does provide a very high throughput compared to the previous standards. It does operate strictly in the 5 gigahertz band, and it tries to reuse as much as the 802.11n technologies as possible in order to be backwards compatible with the previous standards. And it does also coexist with the 802.11a and n in the 5 gigahertz band. Some of the modes that it provides are the single station throughput, which provides throughputs over 500 megabit per second over an 80 megahertz channel, and also the multi-station throughput, which provides throughputs of 1 gigabit per second over an 80 megahertz channel. And some of the new technologies that are specific to the 802.11ac are the 100 megahertz channel bandwidths, which is the 80 plus 80 megahertz contiguous setup, and something that's novel is the 80 plus 80 megahertz channel bonding, which includes 82 disjoint 80 megahertz channels. The MIMO setup was increased to up to 8 spatial streams. It allows for multi-user MIMO and also higher modulations, which you just heard in the previous presentation. This standard now goes up to 256 QAM. It does actually include standard beamforming techniques and space-time block coding and low-density parity check coding. Some of the new applications that are actually made possible by the 802.11ac are the in-home streaming of HD video to multiple clients, rapid synchronization and backup of large data files, a wireless display where you can actually stream a wireless signal to a high-def monitor. It will allow for backhaul traffic, either in mesh or point-to-point configurations. The deployment of large campus and auditorium setups, as well as manufacturing floor automation. So some of the unique design challenges for 802.11ac devices are more stringent requirements in spectral flatness. As you go to really wide bandwidths like 80 or 100 megahertz channels, the spectral flatness becomes more challenging. And also interference robustness. There is a weather radar band at the 5 gigahertz, and the 802.11ac should be robust to such signals. The contiguous band mode, the 80 plus 80 megahertz, requires either multiple instruments for generation and analysis during development, but that also creates issues with additional synchronization in development or testing of such devices. The higher modulation schemes, as I mentioned, 256 QAM, would require better transmitter constellation error performance, and it will require better receiver input sensitivity. So usually what we do is that we have these three different phases, these main different phases in a product development. We start with design and simulation, and this is done again in simulation. It's the first stage in developing a product. And then once we reach to a certain points, we move on to verification and validation. And finally, we move on to manufacturing and test. And in a typical development cycle, during these three different phases, let's say the transmitter IP is first developed in software, and then we have to move into some other platform for prototyping and for verification. And then finally, we have to move on to manufacturing test equipment. And every time we move from one phase to another, there is a new learning curve for engineers. There is more risk in terms of having to debug all the inconsistencies between different vendors or different implementations. So what we've done is that we have taken an approach where we try to use the same IP over all these three different cycles, and we've done that by unifying the IP in terms of the transmitter implementations and the receiver implementations, and we've been able to achieve these by reusing the same libraries across these three different phases of the design process. So to do this, we're using several tools, software and hardware tools. And first, we're using the AWR Visual System Simulator, which is a system design tool that is used for it's widely used for designing of wireless solutions. The second one is the Microwave Office, again from AWR, which is a circuit design tool, and it's really it's used for designing the RF components that go into the RF links for such devices. And finally, we also use the National Instruments and AWR standard libraries that now come for the 802.11ac. When we move on to prototyping, we are performing our hardware in loop simulations by using using VSS, LabVIEW, and NI test equipment connection that's now built into VSS. And finally, moving to prototyping and testing, we take advantage of the National Instruments FPGA and I/O adapter modules, and also the National Instrument test instruments. So the AWR environment includes, as I mentioned, includes the Visual System Simulator and Microwave Office. And what is unique about it, it's the same environment, it's the same unified data model, same database, and you are able to reuse this environment from the very early stages of the design all the way down to layout and EM extraction and verification. And we have quite a number of companies that successfully use this platform. And as I mentioned, VSS, the system level simulator, can be used from the very early stages of developing component specifications all the way down to hardware in the loop. So the NI PXI platform is a very powerful and flexible framework for developing prototypes from the early stages all the way down to verification and validation. As I mentioned, it's very flexible. It offers high performance and also low cost deployment. It does include a chassis. It includes a PXI controller, which is a full-blown Windows PC, as well as peripheral modules that you can use for various purposes. And in this case, we're using a lot of the vector signal transceiver for the early stages of prototyping and development. But you can definitely use a number of VSAs and VSGs, as well as moving down the development path by taking advantage of the FPGA and I/O and coprocessor boards from NI, as well as being able to use any of the amplifiers, attenuators, and switching modules. So What this approach has allowed us to do is that we have been able to move on from research and modeling through design, simulation, verification, validation, and manufacturing, and be able to stay on the same platform and have these cycles that allow us to optimize our development without having to switch back and forth between different environments. And as I mentioned, this was all made possible by taking advantage of the tight integration between the AWR tools, LabVIEW, and the National Instruments hardware. This is just a simple example of our design and analysis at the system level, where we are able to take advantage of the same library, same toolkit that National Instruments uses in their hardware, and we are pulling that toolkit into the simulation models, and we're able to perform any system level measurements by using the same exact library or toolkit that we'll be using down the line in hardware prototyping. And as I mentioned, the next stage would be replicating the same design process by taking advantage of the tight connection between VSS, LabVIEW, and the NI hardware, so we can replicate the same the same test bench, but in this case we include the RF components that we want to measure. And what's important is that we are still using the same test bench, the same measurements, so we are not redeveloping the test bench every time we move down the design process. And furthermore, when we move down to the production testing, we've been able to take advantage of the FPGA capabilities of the NI platform that we can use for customizing measurements in realizing in faster real-time tests. And as I mentioned, the PXI platform is the desired platform that we use, and it allows us to actually do all the MIMO testing that's required by 802.11ac, as well as being able to handle the bandwidth requirements from for the 802.11ac signal structure. Finally, the EVM performance of this platform is truly best in class, and it's a very fast measurement platform. So overall, we've been able to achieve a very versatile framework in developing 802.11ac solutions. And the main thing is that we've been able to reuse the same IP from design through verification and validation all the way to testing, and this has helped our customers cut down the time that they had to spend when they moved from one phase of the design process to the next, and it's allowed them to actually come up with products that get faster to market. We've been able to use the powerful RF modeling capabilities of the AWR tools, as well as the open FPGA platform that allows us to set up fast measurements in production testing. And overall, the main achievement of this approach has been a shorter product cycle and time to market. And with that, I'll try to close here, and if there are any questions, I'll take them either here or right after the presentation. Well, thank you for your attention.